Hang on, everybody. Paul, go ahead, please.
Yeah, my question is, I can download the this thing and open it in like a text editor or something, but when I try and open it in Google Colab, it says I don't have permission.
It should have permissions. Let me check. It has permissions, so it has like enabled with the link. It could be done.
You can also, if you download it locally to your computer and then upload it into the Colab, this is what Jenna suggested, and I did the same thing.
Yeah.
And I think that avoids the permissions.
Yeah.
Did you hear that, Paul? What Gabe just said?
Not really well.
So Paul, the way I got it to work in the or I got it open is I went to Maurice's and then I just edited the address at the top to just go to Drive and it opened up the collab for me. And then now I'm going to load up. Oh yeah, you have Maurice's.
What we said was just to download it to your computer and then re-upload it to the collab.
Yeah, right, but I didn't know where the collab was. I can put it in the chat.
Upload it to where?
I'll put it in the chat.
Yep. So easiest way is just to click on the link, and if it doesn't work, then just simply download it and or add to your drive. And it will show it into your personal Google Drive, and then if you click, then you can open it to the collab and it should work.
Oh.
Yeah. You can be able to see something like this. That means it is kind of open and connecting your computer. So now, if you have already got it open, and if you have connected your iPython notebook, so it will have CPU, or if you are trying to do some sort of heavy computing, you can also choose the GPU. You can simply click on the runtime, and you can click on the change runtime side. So you can see that there is a CPU which is already being connected. There is a Python version. It is given here as well. You do have an option. If you want to do, let's say, dark data analysis in here, then you can also select the GPU. So the compPy can actually work on CPU as well as on the GPU, and it has got both of the functionalities. So you don't have to worry about any of those. So for this particular analysis, I mean, if I'm on the CPU, then it should be okay, because we will be just analyzing one data set per day with this one. So CPU can be able to handle that particular part. So I saved it. So here is a very brief description of what this code can actually do. So it is being designed to get the raw data directly from the website. Once you have the data, then it can actually align the data. It can do the dejittering of the data, and then it can also do the wave analysis. And so at this moment, we don't have any of the functionalities with the polarimetry data, but it is only being designed primarily at the first just to have some sort of the wave track and the wave analysis part. So once you have got still in here, then the first step to proceed will be to install the compPy. So that is kind of very easy. So in here, we do have the Python and all the functionalities and all the libraries that you're going to need. Everything is already being included into the compPy. So all you'd have to do is to just write pip, that's where this is being stored, install compPy, and it is simply just going to download and install and update with all the functionalities you need. So you can simply click here on the run cell. And what it is doing is it is downloading the compPy. It is also checking what kind of the other libraries it is going to need, whether it is related with the machine learning stuff or any other things. That is already getting everything on its own, and it is installing it. So very quickly, you will see that it is kind of successfully installed in your iPython notebook up there.
No, is the source code also? The source code, or is this just an execute?
No, I mean, so if
Open source.
Use Python, obviously. It's
no,
not-
so this is like you don't have to always rely on IPython or notebook. So let's say if you have your Python installed on your laptop, you have your own copy and everything. All you have to do is to go into the terminal and say pip install comply, and will install on your machine as well.
Okay.
So all of these kind of the commands and what I'm giving it here, they're fully functional on your laptop as well. So once you have got the compy in your machine, it is being successfully installed. And the second thing what we need to be doing is to get into the structure of the folders. So the compy needs the structure of the folders for it to look into the data and to save its output into this particular format. So there will be this comp, so the super software, and the output is always going to be saved into the wave tracking output, which is going to be in the comp file. But again, the data is kind of being sorted in terms of the year, then the month, and the day, and then since we are doing the wave part, then we do have the dynamic data. So we have the 1074 the dynamic files, and also we have 1079 in case if you want to do the magnetoseismology and estimate the plane of sky magnetic field kind of thing. So in order to make this sort of a structure, the first we are going to do is to create a directory, which is the comp directory, which is again, so it is very simple. So make directory comp and make directory comp and the wave tracking output. So if I click on this cell, it is simply going to run. And now we have the directories in here. You can also check if you have those directories. If you click on the files, then here you can see you do have the comp directory, which is already in there. If you click on it, you can also see there's a wave tracking output directory also being made in your drive. Is it going good till here?
So how do you get that file synced to the left? Is that
So
under-
here on the side, you will see this sort of a folder kind of an icon.
Ah,
If you click on it, it will show you like where your comp is there and where is your data will be and where exactly your output is going to store.
okay.
Yes.
So if you don't want to like have all the software on your laptop, let's say if your laptop is kind of messy, you want to do heavy computing online, you to use Collab, then all you can do is to put everything on the Collab. It will do your heavy duty analysis part, and then you click download and you can have the final data files on your laptop. So you don't have to worry about whether it is if any of the functionality is installed on your laptop, if something is working, something is not working, if something needs to be updated. So every single time when you're going to do pip install compy, it will get the latest version and all the bugs and everything will be fixed. And so yeah.
It's a nice IDE too. You don't have to pick an IDE, a development environment.
No,
Yeah.
Like you have one.
yeah. 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 So now we do have the folders, then we can actually start downloading the data. So in here, we have got the sample data, which is in the drive, but also you can put any of the data from the comp or the UComp data from the website, simply download it, and you can put it into the folder and you're just going to find the data. So here we are going to start downloading the data. So if you click on the download,
Thank you. So easy. Thank you.
Yeah, thank you.
Yeah, this is very good.
that's fine.
This is the effort that they put in making the notebook work, though.
Yeah, exactly. We recognize that. They did all the.
So if you just click onto that one, so it says pip install gdown. So gdown is where we have it done. So it's going to download it, the Google download an app, and the Google download is going to the drive where the data is stored, and it's going to download to your drives and or into the environment where it is. So now if you click on it, if you have seen something like this one, that means all your data is now downloaded. So if you see here on the files, you can see that you now have in the sample data, your files have actually started getting.
Mhm.
Everything okay till here? Okay, so now we can move. And as I showed before, we need the directories for the comp. So the comp need the year, and then the month, and then we need the day, and then we need the folders in which we are going to put the data. So we have, at the moment, we're just going to deal with the 1074 data. So then we have the data which is already being downloaded, but then we are going to untar it into this particular folder. So by doing this, we are going to create all these folders and untar the data into that particular folder. So the comp is going to find the data and do the analysis plot. If you click in here.
I have a question.
Sure.
Well, sorry, go ahead, because this is, I don't know how long this will take.
No, you did that.
Okay, yeah. Because it was fast for me too. At the top, the cannot save changes thing. If I exit out of the screen, and go back, do I have to re-download the data and remake the directories?
Yeah.
Yeah,
Yeah.
that makes sense.
So this is like what we have done only for this, but because like the data is not going to store. So we don't want all your laptops to be like storing your drives to be filled with data for practice.
Yeah.
So the moment you're going to remove this thing, it will just completely go down. But the link is always going to be there. So anytime you want to play, and so let us say if you have got your own data, and instead of doing this, you can simply put your own data in that particular place. So instead of like having the G down and having this particular link, you can download the data from the website, and all those the FITS file you can just simply put into that particular folder setup. Once you do it, drop down.
So you said the link will always be there. Beware.
Yeah.
Where?
So the link is there, and I can post it online. And we also have.
I mean, it's in the chat right now, but the chat goes
Okay.
away when we get out of the meeting. So
I can share. I think.
well, maybe we'll just send it to everybody just so that.
So,
Yeah.
so on the GitHub,
Yeah, Mike?
Yeah, and by the way, I could archive in the chat as we go.
Oh,
So the
thank
chat
you.
does
Thank
it.
you. Yeah.
So on the GitHub, we have already set up the directory for this thing. So with the tutorials, with the code, and the IPython notebook, so everything is kind of available. So by the end of the session, I'm going to share that link as well. So the code is always going to be in there, and it is already made available online. So now if we have the data and we have the folders, and if we have the data kind of being untarred, it should look something like this, which is the data which we have already got into your folders. Oh, send it. Is it okay?
I don't see that on the left. I don't see the
So if you go
year.
sample data, 2016, and you go to the month, and then you click on the day, and then you click on the dynamics.
It's under there. I see it. 2016. Yeah, I got it. Yep.
So it created the folder for the year, and so basically sort out with the year, month, day, and then the kind of the wavelet that you are being analyzing. So it's kind of easy to find for the compile to locate the data. So far, so good. Okay. So now we have to edit the path. So because at this moment we have been running into your drives, but in case if you have been running into your own laptop, then you have to give the path about this one to find where exactly your compile software is being stored. So basically, it's generally the home. But in case we are being doing it for the session in here, then we are going to edit it. So also you don't need, so the configuration file is like, you don't have to edit too much into it. So everything is being already taken care. So all you need to be actually telling the compile is where the root directory is going to be where it has to find the packages and everything. So that's what we can do is basically run this one. So from the Google Colab, we import the files, and so when we're going to do it, it is going to go into the files for the compile. It's going to locate the configuration file, and then we are simply just going to change it. So if you click on here, it is going to open on the side your configuration file. So your configuration file has the location where your root directory is, number of the wavelengths that you'll be doing, module, your home, your save directory. So you don't have to change much into this one. I can drag it here. So it basically has your directories, and what it has all other parameters that the compile will need to do the wave analysis. So how much the cross correlation, how much iteration need to do. So what are if the input it will require to create the mask just to cover the disk. And so it has got that particular thing done for the compy as well as the QComp, or the comp and the QComp, sorry. And then to estimate the coherence, like what I showed yesterday, it also has everything in there. So in case if you want to reproduce the results, then simply you just need to give that instruction. It is going to estimate the coherence estimates for you as well. It has got kind of everything that you will need. So you don't need to, and again, for the density measurements, it has got the files that it can actually put the Chianti files. So you don't, basically it is kind of on its own. So you don't have to worry about it. This particular software is not installed on a laptop or that is not available, then where to look at. So compy is going to take care of everything. It has got, so just if you have only the compy, it will analyze everything for you. So what we're going to do now is just going to change, I'm going to close this for now so we can see. So the root directory, here we have the analysis. So if you're keeping on your laptop, then yes, it is going to find thing into analysis, which is the generic way compy is being stored. But here we can just change it to the content.
We should just do what you're doing.
So in the root directory, so here it is already been given. So root directory, we have to, from analysis, we will change to content. Home, we don't need any because it is on your laptop. So we simply make it, delete that particular part and make it empty. And the module part is where your Python packages are stored. So either you can do it or you can simply click on it. Copy selection. So the module path. So here it is like in your configuration file, the module path is basically your PyRoutines and the compy. But since we are working on the Google, then we simply give the path for the Google itself. So here we can simply click and
Sorry.
paste.
Yeah, I don't see this.
Step 5, you're on step 5 there. Modify, blah, blah, blah.
Oh, okay, okay.
Oh, step 5.
Yeah.
So I, yep.
And within step 5, what are we doing? From Boulder down?
So basically you change your root directory.
Copy.
Oops. Yeah. So if you, I can do it all over again if you want. So I will redo it. So what we need to do is you have this particular part in here where we are going to edit the configuration files. So then simply click on it.
Wait, is this 5? Step 5.
Right before.
Oh, I'm too far ahead.
Here's step 5, sorry, right above.
Yeah.
And so we grab that file.
So here we have got like what the changes we need to do.
Oh,
So the root directory should be the /content. The home should be empty.
And module path should be copied to the right.
Yes. And then we can just change the module path as
So
well.
that module path, we should copy it to.
Yeah. So that's going to be user /local /lib.
There's significance, whatever, just the link.
Yeah. So you can simply.
User logo. You're getting used to passively clicking.
Okay, so we need to turn the number past.
Something to, so they just locally do something.
This over here is telling us what we're supposed to. Thank you. I was confused about which had to go where.
Yeah. So it is right here that we also make the changes.
I mean, maybe.
Number 9.
So if you just made the changes, then you can simply close the config file. Yeah.
And then go back to.
Oh, then you don't need to go anywhere back. Then you just go forward. So it has got everything updated, and you don't need to recompile or do anything. It has already taken care of everything. So now we are going to. So the first thing that we need to do is to jittering of the data, right? So we need to select a region where we are going to use so the compy is going to use that particular region to align all the files. So if any of the jitter is already being present, because in the wave analysis, if there's a jitter, that can be a false thing. impression that there is a wave in there. What we generally do is we find a bright region where they have a gradient. So we have a bright region and which is having some sort of, if you just do, if you can check by gradient or simply it should be a bright and the dark region combination, an edge of, let's say, loop or something. If you simply find that sort of a region, then you edit you can give the compy what are the regions that you've already selected. So here we have already done that. So what we need is basically a date, then the coordinate x, x2, x1, x2, y1, y2. And then again, if you have all the data which is being stored in your performative compy, but you just want to analyze a particular portion of it. So in some of the times, let's say you have a gap or you have the data which is being, you want to avoid a flare in, let's say, in some instance, if you want to do the wave analysis or something. All you need to be doing is to give the specify which sort of the file number or the frame number you want to start with and what sort of the frame number you want to end with. That's it. So here what we have given is the date, which is the 2016, 10, 14. And we have got the x1, x2, 3670, y1, y2, 230, 295. And then the start file is 0. And the end file, the number of the files that we want to process is 50 in total. So then this is, so that it is going to go into an Excel file that is the compy is going to use when it's going to look at for the de-jittering process. So you're going to see it now next. So what we can do is,
So just to give people some background, so this is to de-jitter
Yes.
the
Yes.
data set. And the way we've done it in the past is you pick a sub-region that has a
Yes.
lot of loops that are both vertical and horizontal, that's gonna use
Yeah.
to cross correlate and to latch
Yes.
on to them.
yes,
Now, this is the one thing that has been an obstacle to us, making this an automated kind of pipeline.
okay,
Like, because we would like
Yes.
it to not to have to tell it where to look.
yes. So at this moment,
Right.
it's still a bit manual. That's where we have to,
Exactly. So, I
Yeah.
mean, it would be nice in the future if we can like use an annulus around
Yes.
the image.
Yes.
Where it would have all that information.
Yeah.
But it's really tricky, this stuff.
Yeah.
Because if there's any gradient in the intensity going outward,
Yeah.
it's gonna latch onto that gradient rather than the features.
Yes.
So you have to sort of like high pass filter the image, maybe.
Yes. yes,
Do some kind of stuff to it. But this is something we'd love to
okay,
update with UComp so that
Okay.
it can,
Yeah.
it can just sort of take the whole thing, but and I tried working on this some, and it works for a while, but then Corona's changing, so.
we try to have this thing, but the problem is like when we just ask the Python just to look for any of the bright feature and stick to onto it, then if there is some other bright feature that will come, so the code is simply just going to jump onto it. So it needs a sub-region where it just want to locate itself. And that's the sub, so we can't actually say, look at the entire field of view and to find something. Yes.
At Juliana and John's request, my team is working on this.
Okay.
So
Right,
we
thank you.
expect an update. We don't have anything today, but wait another week or so.
Great.
Parachute, yes.
How, I mean, by experience, how large this subregion should be to get a good alignment? What typically is?
I mean, so when we have the sub-region, we are going to put it into the Fourier domain, and that's where it is just going to
Because,
do.
but how large?
So
this-
it should be very large. It should be like, so like what I generally do, I don't go very far away from the limb, but again, not very close to the limb, because that's where you can have any of the changes and everything. It's not going to find. So it's like, and the size like in here that you can actually see, it's again, 35 pixels and so 35 pixels in X and Y, or maybe 35 to 50 pixels. So that is the general rule that I follow. So,
Not very many.
so you can just like, so
So what does those numbers mean? Are those the?
yeah, so
the
it is,
coordinates of the corners?
yes, yes,
So what, the 3670 is the XY coordinate of one
so,
corner?
yeah, so
And
you,
then
you have,
3295 is the other one. So
Yeah.
that means these boxes are about 200 by 200.
no, I mean, so we have the X1 and X2, so 36 and 70 and
X1,
X2.
X2, very good. Y1, Y2.
Yes.
It's pretty small.
Yes,
Yes, that-
it's a third.
That's very interesting. Okay.
Yeah.
This is almost magic to me that they can pick such a small area.
Yeah.
You assume it moves everywhere all the same.
Yeah.
So we're on like a rotation.
This part's not focused.
So we're moving there, getting the worms.
This part's not.
No, it's not.
So if you just simply click on it,
I believe that.
What error are you getting?
Rotation, are you worried about rotation?
are you getting an error?
Well, not an error there, but if you go to load data to the next step, then it says the beginning kind of.
Okay. So in here, so the next step is going to, so like if till here everyone is okay, then we can move the next step. It's like
Do we
basically,
have to,
But what's supposed
we
to
have to
happen
run
after
that?
that?
Step
Yeah,
yeah, you need to run that.
One, step
but
five.
does anything happen from that one? Nothing.
No, so it shouldn't be doing anything. So basically it stored the coordinates that we are going to use in the future.
And it doesn't matter if you do it like 10 times.
That's fine. Yeah.
If I have.
Don't worry. You can keep on changing. You want a different region to go live, a different box size, that's fine. Don't worry. So now we are getting to loading the data into the comp. So from the compPy in out, we are going to import the load initial files. So all you need to give is the date that you want to do.
I've already.
So you give the date and then you, and then it's going to find your where the data is being stored for that particular date, and then this is the interpolation. So let's say you have a data gap, then how much data gap you want to cover. So if you have a large data gap, then you don't want it to cover because then you are creating an artificial data set. So what we just want to do is, let's say when you have a one frame missing or one bad data frame. So when we just tell it, let's say interpolation limit is 3, then it is going to say, well, okay, I have found this bad data frame and I'm going to remove that bad data frame. Instead of that, I'm going to interpolate just to make the data smooth for the wave analysis. This is it. And all that particular part, it can just do by one line.
So I'm getting a thumb on that.
Yeah,
Okay, so
I should run that then.
yeah, I think they're probably getting this error.
Yeah, I have some error.
File not
Weird
found.
analysis.
It's
Wait,
find dateinfo.csv.
No, no, I got it wrong.
Okay. So now I know what the problem is. So if you go back a few steps up, while this run, I can show back in here. Did you change your root directory to /content?
Where's the, which step? 4?
Yeah.
Yeah, step number 4.
In the config.
Maybe I have a different problem than like,
Root directory equals /content.
No,
Yeah, root directory.
So if you click on the modified path,
Python 3.10, this package, what?
Now it's coming. So root type.
that will take some while because it is loading the data and saving the fixed file at the moment. So,
So when I click on that one, it takes 0. Actually,
okay.
which one is it? Step 5? No, it's step 5, sorry.
Yeah, so if you go on the step 4, then it tells you like what changes you need to make.
Yeah.
And on the step 5, if you like basically on the step 4 itself, if you click, then you're going to find your config file.
Maybe, I mean, I don't know, is there a way to know if you've gotten this right?
Okay.
So for me, this reading data works.
We're all having the same problem.
Okay.
I think.
If you
It's fine.
no.
Oh, you, Windows.
No, not necessarily.
With my Windows, it worked perfectly fine.
Yeah, for me also.
Oh, okay, good.
Wait, now it's
What a bummer.
working
No.
longer.
Oh, it's, yeah, I think it's working then. It's taking a long time and I think it's working because
Yeah,
that's what
because
happened.
I got like already
The
the,
problem is
it was another that
3.10.
home then.
Yeah.
the
so you have to check like what the module path you've been giving. Maybe your module path is wrong.
Yeah, check your
I'm checking
module,
that.
I mistyped mine.
All right, I copy pasted, but.
Yeah, because if you're copying pasting, it may give error.
Show which home.
Because
Oh, I
it is
Yeah,
copying the
Fine.
instead of
Yeah.
copying the text.
This package. So now I go back then and I can get out of that.
Just
Just read it. Oh, could it be the smart quotes?
Probably it works now.
yeah.
So I did that.
I was able to copy and paste the quotes and everything. and
I was
everything.
not, but
This
my
one
computer.
and go down,
Oh, good point. It might be a computer. Yeah,
I
good
know why.
point.
and then now there's this.
Yeah, I think you're right.
Do not come to US with such computer.
I got it from my boss. Fortunately,
I want to retype the whole thing, Steve, if you have
I
another.
don't want to keep it.
Where's
Okay,
the-
so again, it's having
Where's
a
that?
problem.
Yeah.
It's not changing your. Can you check again?
Works for the win.
So we.
Restart.
Type
No, restart and run all.
But did it work?
Yeah, so somehow it just was
So here.
getting bad.
Out.
Oh, restart went on.
Yeah, so I ran
And then
this,
click on the config.
I ran it all earlier before making that edit. Somehow it saved the wrong answer.
Mm.
How do you do the restart? Restart run on.
Yeah, runtime.
I'm having to run on.
Yeah.
I'll restart. So go to runtime and do restart runtime and then go to the top.
I don't have to do this.
No.
Because that just brings that up. to-
Yeah.
I'm on, oh, yeah.
Yeah, there's probably a better way to do this, but
Oh,
Yeah.
in IDL, that's right.
Yeah. it's like, okay, well,
Yeah.
fine, let's see what that.
So that looks,
Go back to the
that
very
looks right.
beginning.
Yeah.
We'll do the, and then, but do the restart first. We're just trying.
What did you do? Turn it off at all?
Yeah, I had a typo in my config file, and now I'm doing Thursday, restarting and trying to do it.
Yeah.
And then this was interesting. The warnings.
That's one.
I'm just
For shame.
There was what,
Okay.
Yeah, it's,
Just like.
Just do everything. Yes, it worked. It worked.
Okay.
So, restart.
Turn it off and on.
Okay,
Yeah,
So step one and then go back down.
yeah, so just keep on clicking all the steps and then again, make sure that you have made these changes on the one.
It's fine.
Because the wrong shape.
No, it says that there's not asking about it.
Oh.
Then just.
Oh, yeah, I've seen that too.
He's got the same error on that when he done it.
There's a question mark.
Why what? I smart quotations. And if you don't have it, and I don't know.
Yeah.
The change of.
Just do like a checks, like the requirement you have.
And I guess in Windows, they don't
Yeah,
have the same
just
smart
seen that error.
question mark, smart quotation or presentation between text. And so I went back and rewrote it with the typing notes.
So how many of us were able to load the data?
It's
Is everything working?
still, yes, but it's
Okay.
not fresh.
Okay, so now if we have the data which is loaded into, so what it has actually done is it has actually took the data, it has got the header information, it has got your all the kind of the data which was in the file. So it has taken your intensity data, your Doppler velocity data, and your line width data. It has got taken care of everything. And now what we are going to do next is we are going to check where exactly the data is and what exactly the cube actually looks like. It has made a cube of that one. If you click here, which is the cube.keys, that will say what exactly your cube is having. So here what we have actually done is we have read the data, it with the load initial file, it has made a cube and what the cube is actually having. So there you should find the data, your header information, and your primary header that you're going to need for your future. So when we say the cube for the data, we have the 3 cubes in there. We have got the cube for intensity, we've got cube for velocity, and we have also got the cube for the line width. And then for the headers, we've got individual headers for the intensity, velocity, and the line width. And also we have the primary header, which has all of the information. So we can check what exactly is what we have got into the primary header. You can say in the primary header is basically from the cube. We can just give the key, which is the primary header, and then we can simply print what exactly in that particular key. If we do it, and it will show you all the information about your data set from the header. Okay, so you can see the time and when the data was being taken, all the information that you might need. And everything is in there. So now when we do have the data which is now being sorted, data is being read, and now we have got intensity, velocity, and the line width kind of thing. We have got the header information, everything. Now we can play around with some sort of a kind of the display to see what exactly we got into the cubes and how the data actually looks like. So this is just like what we have defined a small function. It is going to give a pretty plotting kind of thing. So on the X and the Y, you can get the arc second. So instead of showing anything into the pixel, we can just get it. So if you click in here, it just takes, so it will just go into your header. It will take the information, a number of the pixels that you got into your x-axis, number of pixels you got into y, and convert that into some sort of understandable information, right? Now, so even once you have got the data, the cubes, the cubes are already being stored separately in your folders. So what you can do is like now you can input, like you can load and the cubes into your file. So you can say from compy, input output, it says save and the load and import CPU load bits. You need the matplotlib and the sunpy for the visualization thing. Then just to plot it, you all need is your date. So you give the date to it, and the easiest way to do is like the data cube is CPU load bits date. If you can do it, then it is only going to plot your intensity file. So that is the default behavior into the compy. So whenever you if you want to just see what is happening in your data, and you don't want to worry about your velocity or any of the information, and you just want to have a quick look, then you simply need to do a CPU load bits, bracket the date, and it's going to give you intensity files. That's it. But in case you want to see the velocity and the line width, then we have to do is basically the data is basically the cube intensity. Like here, what we can generally do is we can read the cube intensity like this. So cube intensity is CPU load bits date, but then there we can actually assign the key. So I is for intensity, V is for velocity, and W is for the bit. And these keys are actually coming directly. If you have seen this in before, here I have already shown how the data structures are. So I, V, W actually represents what you have, the intensity and the cubes and thing. So all you have to specify is in the bracket, like which kind of the key you want to do. So if you just say I, V, and W, it's going to simply find it for you.
Can I ask a question?
Sure.
Scroll down to where you have that data I.
Yeah.
There. Is the number sign a comment? And if so,
I have to sign.
and is the cube int then not defined? Or this is my ignorance of Python.
Okay, so if
I have the same.
Yeah.
you click on it, then
yeah,
yes,
same
it
error.
is giving you the problem because it has not read the data. And you can,
Uncomment.
Comment? Okay.
Yeah.
Cool. I like it when there's.
all of them.
All three. Yeah.
so like maybe while testing, Richard might have actually done it too, because he's already read
Repeat it out.
and you can do it all over again. And it's
Oh,
like
yeah.
that by the reason. But if you uncomment it and run it, then it is going to go into your CPU load bits. It's going to find the date. It's going to load your files, and it's going to sort it all the intensity, velocity, and thing. From the intensity cube, it will go to the keys are data and the cube I, and then you'd assign some sort of frame number, kind of the color match that you're interested in, and the access labels, and get the pretty picture. So it is going into your folders. It is looking out for where exactly what your process data. So data processing is already being done, and it has already stored your bits file into that, and voila, you got your.
Things I'm hoping like this noise. We know it's good. So we pick, you'll come to this later, sure. Pick it and it's the region. We get like, you think that's the one that.
Yes, so this is the first step when we just plot it, and now we will go to the de-digitering process.
Okay, so.
So we have not done the de-digitering yet.
So what have you done though?
So what we have done so far is basically we have got the raw data, and then we have actually processed that particular. So
You've done the wave direction.
Yeah.
Without degenerating.
yeah, so at this moment, no de-digitering, but it has found if any of the gaps are in the data set, and it has removed that sort of a gap. It has taken care of all those kind of things.
But it's done the wave direction.
No, it is not the wave direction.
Oh, so what is that plot then?
Then it's the bit.
Oh.
So here you got
What is it?
the intensity, the velocity, and the
Velocity.
Yeah.
And that's without degenerating.
yes.
Okay.
So this is for the quick look. So now you can select the region that you are interested in. So let's say you want any of the,
Well, you're interested in everywhere, right? Well, you're saying for degenerate
yeah,
to use as
a small region.
as that small region.
Yeah.
Or to lock onto.
Yeah. So at this stage, we are just at the quick look stage. What we have done is downloaded the data, we have made the cubes, and from that particular cube, we have actually sorted out. So basically what the compy is doing till now is sorting out the data. So it has got your raw data, and instead of like looking at all the files individually, it has kind of combined, so it can find all the intensity, velocity, and the line width files in one particular. Once it is done, now it is going to do the dejittering process. So the kind of the kind of the region that we have defined before, if you want to redefine it, then still it will work. So it's not a problem. So now we will go to the dejittering process. So here we can show like how exactly what the region actually looks like. So we can, so these are the coordinates that we have actually selected from that particular file. And if we just plot that particular region, here is the intensity images, and this is the filtered image. So what we have done is a solar filtering.
What is the definition of this?
And the line with pandas.
Yeah. What?
It's in step 5.
If you go back into step 5, you can see here.
The numbers of the subregion?
Yes.
Yeah.
Yes. So if you go up here, we have actually already given the date, the X1 and X2 coordinate, and the Y1 and the Y2 coordinate, and the start file from which you're going to start.
Okay.
Right?
I remember now.
Makes sense?
Okay.
So here we have stored all the values.
232.95, selected that.
Yeah.
That's the region that you're showing.
Yeah. Yes.
And why? I used to have an interactive thing where I used to click on one corner and click on another corner, but my regions I used back in the day
Yeah.
were quite a bit larger than
Yes.
this tiny.
Yes, so you can make the larger, anything you can play around with.
What kind of filtering is Sobol filter?
I think it just shows you the gradients.
The gradients.
Yeah.
And why would the gradients be the thing?
Because we just need if the gradients are higher in that particular region, then in the Fourier domain, it will be easier to pick up like.
The Sobol filter just shows you have a region some shading features.
Yes. So
Yeah.
if you just look at the intensity image, it may look fuzzy, and you may not be able to pick up whether it is a region what you are picking.
So that filter is only used to select the region. Then when you do the correlation, you go back to the original data. Is that right?
So what you do is like here, you just do a quick look image. So you plot all these images, and then whatever the region you are interested in, you kind of choose that sort of the coordinates manually, and then put the coordinates in here.
But the code actually that aligns the image does not use the images with the super filter. Goes back to the original image.
It's like a cross correlation in Fourier space.
Yeah.
Which is something Steve Kyle showed me many years ago.
Yeah.
That I implemented. It's very, very fast.
Yeah.
But when you don't, go back to that subimage. The thing that worries me is you see how such a gradient across it. I mean, even though there is sharpness in there, the Sobol filter picks up.
Yeah.
There is also there's a general intensity gradient.
Yes.
And when you do a cross correlation, it picks up on that gradient.
Yes.
Not on the
So
features
what it does, it actually does the solar filtering, and now it has got this bright region, and that is what it is going to use for the track.
What do you mean? How is it just going to use that?
So in the intensity, it will actually find the bright region in here. So let's say this is the region what we are kind of interested in. So you can see here the pixels are very bright, and here the pixels are not so bright. So this is the kind of the region what we are actually feeding it, like where it is going to have this sort of a strong bright and the black, and that so this is the kind of the bright and the dark feature that it tries to correlate with the next image and the next image in the Fourier.
Yeah, so that's. I'm sorry.
You avoid the culture.
Yes, we avoid the
You avoid this culture. And then if this is the structure that's moving, sometimes we don't see. That's a problem.
Yes, that would be a
So
problem.
you have to be careful what was hitting.
Yes, and that's the problem with such a small region.
Yeah, exactly.
So this is why we have to manually iterate a number of times just to find the perfect region.
So there's the intensity. There's a Sobol filter there.
Yeah.
So now you're going to go and use what? So you're going to take the Fourier transform of the intensity
Yes.
in that whole time series
Yes.
of this region
Yes.
of these coordinates.
Yes.
You're going to take the Fourier transform.
So what it's going to do is to like take the region and take the Fourier transform, and it is going to calculate the shifts. And once it has calculated the shift, it's going to apply it for the entire image.
Oh, do you take but you do the cross correlation on the Sobol filter, right? Not on the intensity.
It takes the intensity.
Oh. So then what's the point of the civil filtering?
It's just to be sure, like if you have the right region.
Okay.
So it is just like another way to check, like a double check onto like whether you're looking at the right, because like if you're looking at the entire sun and maybe there are some regions which in the intensity may look all the bright and you may not be able to find like, okay, what you have been looking into. And some other regions may look like entirely fuzzy and you won't be able to make anything out of it.
What if you did it on the filter image? Would it be sharper and better, easier to correlate or no?
But that's a derivative. It's
Yeah.
a derivative image. It's.
It's not-
Yeah, but it shows the
Oh,
edges.
you're right.
So,
all
I mean,
the
there's
all the
still-
subtle filters.
Yeah, all of a sudden.
Yeah.
I just curious.
My experience, I tried to do some kind of masking, I tried to do the correlation and changes the intensity enough that it don't
Yeah,
actually
just
get,
more.
it
Okay.
works better on the original.
Okay.
I've used unsharp masking of my subarray,
Yeah.
so to speak, which just brings out the features and gets rid of that
Yeah.
intensity grading, which I think you really need to do.
Yeah.
And it helps a lot,
Okay.
but it doesn't work all the time, you know?
So my experience with, especially with comp where you had worse or good days with ideal was that without the sober filtering, you're kind of hopeless in the worst surface. So you need to sober the entire array and do the jittering on the sober array to even have a chance of doing it.
So you're doing the correlation on the Sobold array.
On bad days, it doesn't work if you don't do the sober. So it's
So you will have more gradients then. On the bad data sets.
And so you're doing the Fourier transform on the intensity. You're just looking at the Sobold.
Yeah, so we are just
Reassure you that
Yes,
it's an
it's
area
a-
that's got a lot of
double check.
contrast.
Yeah.
That the cross correlation will
Absolutely.
latch onto. And you're actually using the Sobold thing, like what Jenna suggested.
in some days it's you can get the correlation otherwise. In some days it works with just the intensities. It depends on how good the sky was and the actual observing sequence was. But that was the ideal. I'm assuming it's kind of the same with Python, right?
Absolutely. Yeah. So this is why this particular part is still manual. You have to manually look at the images and then find, okay, which is the region which port is kind of a stable, it's not changing much, it's not having any fun going around.
So in your experience, like when you play with this, finding a subregion and line it, what is that prevents some days to be aligned and why some days can be aligned nicely and some, you know?
Well, if you have a good data set, then that actually solves many of your problems.
But define good data set.
Yeah.
What is the block?
So
Is that
the
the data gaps, the data gaps,
So the
the clouds?
data gap is like if you have a very huge data gap, then we don't use for the wave studies, because then, like, let's say if you have a few missing frames and like quite a few missing,
Then you cannot
then we cannot do any wave analysis because you can actually interpolate between that, but then that means you're creating an artificial data.
Yeah, that's.
And that means that what the wave kind of the feature you'll be getting may not be correct, and you are guessing that it should be a linear side of a jump from one particular grade to the another one. So if you have seen that when we are reading the cube, we just say interpolation free. So that means it's like it doesn't go very far. You can change like from 3, you can make it 10, you can do anything, and it is just going to interpolate as much as you like.
But 3 is a safe way to go, but for the jittering, what in your experience is, why the jittering works for some days and one it doesn't work for some?
If the data is kind of a bit more stable and the regions are kind of very much clear that we have been looking at, and as I showed before, like we do have the gradient, like we just need a bright region. That's it. And then we just so this is just an add-on. The Sobel filtering is not like a part of this thing that you have to do. It is just to be a bit more sure.
But it might be a good thing to do.
Yeah. So
I mean,
it will just give you a bit more confidence that okay.
I had a question on the data gaps. What's acceptable to look at? Time frame,
Ideally-
time frames. What would you think is reasonable? Where's the line between reasonable and not reasonable?
Okay. So ideally, no data gap should be there because of the wave analysis. So it depends on what kind of analysis you're doing. So let's say if you want to do some sort of CME analysis or flare analysis, then if you have some data gaps, then you know, okay, like this could be the process. But with the wave is like when you're going to do the wave tracking, at that particular stage, you need a continuous data that it is going to go forward with. So what we generally do is we don't go till like 5. So if there is, let's say the 5 frames are missing, we kind of avoid that particular part. And this is what, like in the first, if you have seen that we can define which sort of the frame number we want to start with and which frame number we want to end with. So generally, like in most of our analysis, we don't have all the 350 frames. We have, let's say, always 180 where, so what I generally do is I see where the data is kind of big available. I just only select that particular region. And then 1 or 2 missing frames is kind of okay, because that's where we can do the interpolation and thing. If it is like 5, that means like multiplied by 30-second cadence. That means you are kind of interpolating a lot. Let's say over a minute, you're not having any data and you are guessing technically. And for the wave analysis, but then if you just want to abuse the data more to like for the magnetic field information or anything, that means it may not be able to give you the correct phase speeds or any other information. And so in our analysis, we kind of avoid that sort of data set. So this is why you've seen, like yesterday in my talk, we didn't add like the coverage for the entire solar cycle, because even if there was some of the data, then we cannot use it. And the data is already there, but to find the right kind of data set which can give you some sort of reliable information. Yeah.
So so the temporal cadence, so interval between the images is 30 seconds, right?
Yeah.
I have a comment in the question. Comment is, Seth, later this morning, it'd be great if you weigh in on what is your minimum wave, like 30 seconds. This is going to come up. And what is the duration? You have to have an hour, you have to have an hour 15, that will come up.
Yeah.
Sure.
My question is this difficult at solar minimum, where things tend to be more amorphous, you don't have as many sharp right structures? Have you found it more difficult just because the coronal structures?
Yes, because what we had looked at are the loops, and they will be always be there. So I mean, like we don't need like very strong kind of a feature. I mean, all you just so at this particular stage for the jittering, we just need a bright region, which is in there. So like in here you can see that the bright regions are bright on top, things like that. So like so again, like this an additional step is it will tell you like, okay, that you're looking at the right place or not, but you don't need like a very obviously clearly defined or something. That's something that you don't expect. But the UComp, yes, we do have really very clear features because of like the kind of the pixel size now has been changed that we can really make out. Even with the comp stuff, we can make out quite a lot of the features. So the kind of the data sets what I actually done with it was you can always find at least one feature which is in there, which is kind of stable, not being.
Sorry, I have one more question, but
Go ahead.
this jittering is such a critical step for us going forward because we need to do a lot of sampling. So I keep hearing that in some days this co-alignment doesn't work.
Yeah.
If I understood correctly, you said that you need to start with a day when the data are already co-aligned pretty well, and then you kind of refine it and make it better.
Yeah.
But if the data start to be from the beginning, they're very misaligned because we had problem with pointing or there was wind, then it doesn't work. Did I understand correctly?
Yes, because like let's say you put a slit and you try to get, let's say, time distance kind of a plot, then if there's a jittering or the frames are being shifting, and then you put a kind of a slit onto any of the data set and you get sort of that is going to give you a sort of a wavy structure anyway. Now, how are you going to interpret it? Whether it's an actual wave that you've been looking at or you're looking at a jittery image.
I get that, but I'm actually going back to the instrument, how the instrument works.
Yeah.
So to correct for it,
Yeah.
if I understood correctly, I keep hearing from people that the jittering doesn't work every day.
Yeah.
So I'm trying to understand why it doesn't work every day, because we would like to make it work.
The seeing sometimes is worse, or there's,
Yeah, but in principle, we never have shifted our model to pixel, right? So we should be able to correct all that.
Yeah.
But some days this technique to finding a region, even in the bright structure, doesn't give you a good alignment when you run the digital encode. So I'm trying to understand what is the reason why it works on some days and it doesn't work on some days, because
I can show you, but not now for the 2 days that we're working on, how much the co-alignment corrections affect the entire dynamics data set for a particular
I believe that
day.
part, but
And you will see that it moves a lot, and the correction is discrete. So then by correcting, you're introducing small perturbations. So
Again,
I
we
know
need
what
to
you're
start
asking.
with fine data, and if the data are not aligned well from the beginning, you are not able to correct for it. This technique doesn't work if there is.
It might be just, so based on how I saw it, it might be just a blustery day in terms of wind. And the frames move a lot. When on a clear day, the whole
It's not like
alignment
it's not
setting stays vaguely stable, except a few data points. So you can see it, and I'm expecting if we run the jittering and the waste program on the 2 days, the clean day would be way faster to call a solution.
Could it be that you're smearing within an exposure time, so you
Yes.
have a blurrier image to begin with,
Yes.
on a blurry day?
All
Yes.
of that.
So
All of
then,
that.
you know, you don't have a sharpened image to co-align, so it
Yes.
just doesn't work as well.
And it depends how, it's a cumulative things, how many frames out of the total are nice and sharp. I think that's the issue.
Elena, you and Vanessa are gonna show us that next week or whenever you're ready. You may want to ask other people here if they want to join a virtual meeting.
So what I'm hearing is we really need to do better at the telescope. That if for some reason the tracking is not good at the telescope, you can, even with this technique, you can realign things.
And we also discovered what you are suspecting. So at the camera level, at level 0, the main, at least for these 2 days, you kind of correct everything in terms of distortions from the camera, except the scaling factor between the cameras. And that adds additional blurring. And we started quantifying that scaling factor, and we want to produce an ad hoc correction to the scaling between the two cameras. So it's probably a distortion thing, because the beams optically should be the same.
So what's the, I'm sorry.
So if you have 150 frames, only about 30 to 40% of them are actually have the same scale in them. And the other 60% are scaled in discrete units of 1 step from perfect scaling, 2 steps, 3 steps, which I don't know if those are pixels or not, but it's discrete. It's the way we did it gave us a discrete interval.
So when you said your steps, so you're saying the image goes like boom, boom.
The actual scaling, so the occulters,
The
the frame are of different sizes.
The occulter shifts in size discreetly.
Yeah. But that discrete might come from our method or might come from the data. I'm not, this is the part that we're still looking at.
Can I maybe suggest something which is a little bit different? We occult the disk of the sun, but we can't see the disk of the sun because we get rid of it. But during the course of the day, the sun starts to peak out and the observers then move the occulter. Discreetly, boom. And they do it maybe a few times a day. But when you
sorry, I don't have a plot.
when you de-jitter, then the corona stays in the same place and you'll see the occulter. When we give you the data though, we align them all, we make the occulter be there.
Yes.
So what happens is the occulter's there and you'll see the corona go boom, boom, boom.
He's looking at level 1 files.
0.
Level 0 files.
So step
11.
So
There's nothing I can think of that would make the plate scale change discretely several times a day.
it's really weird, but I don't think it's a physical thing. I think it's a correction thing that introduces this thing. I think it's from the distortion.
Well, if you're working at level 0, it's uncorrected. There's no correction.
No, we're at step 11 of level 0.
So he's looking at semi-process level, level 1 data. So it's not the complete level 1 processing, but it's got the debanding,
everything except the
UCOM level.
Not quite 1.
Not quite 1 either.
So we took Mike's
I've got all the data on my disk, and I do not have a not quite level 1.
You don't have a repertoire. So in Mike's pipeline, right before we add the 2 sides together, we saved a FITS file and gave it them. So it's got everything except
it's not quite level 1.
Yes.
So we can talk offline about this, but and I think
Still, there's nothing I can imagine that's going to change the plate scale. several times
It
discreetly
shouldn't be
during the
several
course of the day.
times. Should be
It's not several times a day. 60% of the frames have this problem.
always.
In the 2 days that we have,
You know what? Sometime maybe next week, show me what this looks like. And we'll have, because it could be a problem.
and it fluctuates. It's not like it stays constant and then it goes away. It's you have 2 good frames, then 1 bad, 3 more good frames, and then 7 more bad, and so on. So it always
System.
I don't think so. Also,
You don't
I'm
think
curious
so?
what happens next after this
Yeah.
for
Okay.
compy.
Yeah.
No, I have a question. Sorry.
Sure.
Last one. So how do you pick the data? You start with the date you are interested in, and then at the end of the analysis, you said, I don't know, it's wrong date and pick up another day or what? Or look at the data at the beginning, see that you have nice sharp images, whole series, and then start the analysis?
Yeah, I mean, like, so in the code, we have to get the data first. So the compy can actually look into
Okay,
it.
so at the end, you know that.
So let's say if you don't like the data, you download more data.
Mhm.
And you know the structure, like the year, day,
Yeah.
and the
Yeah.
date. And then you can just simply give the date equals to 20 something or month and the day, and the compy is going to look into that one as well.
Okay, and since there is no need to have very bright structure, is it possible to do such analysis for cavity?
Yes, I mean, but at the edge of the cavity, you're going to see the bright region.
Yeah, but
Yeah.
still we have bright,
That's fine.
bright loops. I don't know how to avoid the occulter because.
I mean, so you don't like kind of like get very near to the occulter. So like what I generally do is basically stay at least 5 pixels away. From the occulter.
Okay.
Yeah, so
Even if-
even that region,
Yes.
so if this is the occulter, you just pick a sub-region.
Yeah.
Away from the occulter.
So even if it's going to shift the
Here
image,
or
it is
here
not
or
going to
here.
touch the occulter anymore.
I see. Okay.
But this is the fundamental problem. Using such a small subarray, this seems to me like, I mean, I see the corona just evolving all the time. So, it's
Magic?
not gonna work.
It's counterintuitive. We expect
I
a
wish
much
it were
larger
magic,
region.
but it's
Yeah,
not.
it hurts. So yeah, this is like just for like selling for this particular session. It is not like a very hard rule that you should have these many pixels, or if you give a bigger region, that the compy is not going to work. You can give any number of pixels and it is still going to work. So that's not a problem.
But the bottom line, what I'm hearing is that we need to do a better job at the telescope, because if we don't, then you can do your magic, but there are chances it doesn't work.
What if you just had a tracking, like, you might not need to do a better job in real time, but if you had like a real small, like crappy telescope with a solar filter over it that just looked at the disk, like,
We do.
and can't you use that to do this
Well,
little one?
It's a diode.
It's a diode. I mean, we
It's
look
a
at
constant, right?
But what if we have chroma?
Okay.
We'll have actually good images of the disk.
So then, if that's experiencing the same, it's on the same mount, right? So it should be experiencing
Yeah.
the same jitter.
Well, yes and no, it doesn't experience the flexure of the spot.
That shouldn't matter though for the fast corrections.
But, I mean-
Matter, but
So like the way that we do our tracking on the airplane is we do a solar filter on the either the edge of the moon if it's during the eclipse, or the edge of the sun if it's a test flight. And of course, we get a really nice sharp image, and you can very easily fit a circle to that. It's like the best case, right? So then you can get really precise subpixel shifts, and it works very, very well to co-align things either in real time or post processing.
we should really, I mean, at this point, we wouldn't have chroma, but maybe the diode is not sufficient.
Jenna's telescope probably cost 200.
$100.
Yeah.
Yeah.
It's not the cost. I mean, you add space and then we need to put it.
It's big.
this,
It's a little, yeah, the one that we use for tracking is like 6 inches long and like 1 inch wide. It's because it fits inside our secondary obscuration. So it's a real little.
I mean, the guider could produce this, but we don't save any information from it at a high enough rate to know anything useful.
But our SPAR guide.
Yeah,
And I think, let's just take that as a given and talk about how to do it, but I think, we'll get back
Let's go
to
back.
this. But this is really good discussion.
Yeah, so now we can do the PG trick first. So here it is like so the comp is going to get the files and it's going to get the code, which is the PG trick. It is just doing this kind of in the Fourier space. So what it does is basically the file path is going to tell us where exactly to look at the files. it is going to find the files. If you already know where the files are, then basically cubes align is digital and then file and the date. That's all what you need to give. If I click on the run cell, then what you can see, it is searching where exactly the process data from the cubes are. It is looking at that particular file. It is loading all the files, and then it is feeding into the digital code, and it is going to estimate everything. But this may take a while, but yeah.
So one question while this running,
Go
are
ahead.
you cross-correlating one image with the next or one initial image with all the others?
So it is just like the cross correlation of the one image with the
With the next, so it's kind of a daisy chain.
So if one of them messes up, then it's gonna cause a.
Yeah.
And
But you could.
if you interpolate,
cross-correlate.
do you use the interpolated image for the next one, or do you use the last real image?
Well, if you don't have the data gap, then
But if there's a data gap, are you using
it is going to take the
interpolated image?
Yeah.
Okay.
So the first command that we gave the cubes, and we said like, okay, so the initial stage, the load initial
Yeah,
files.
okay.
At that particular stage, the compy has already
Built
taken
in.
care of everything.
Okay. The DJiter just looks at that, doesn't care where
Yeah.
the source was.
There's a second
Meanwhile,
check. You
I
can
can-
also cross-correlate the first and the last.
I think then
you're
checking the
done-
first and the last page is how
Yeah,
well
you're
it
done,
is.
but then that'll tell you how well.
This is a circuit to check that we can come out with that automatically.
So if you click on the wave tracking output, maybe it will, yes, here. It also shows you this. So then you can easily find where exactly the files that you are interested in. So this is
Okay.
kind of a bit messier one, but if you do it. on a
This is
laptop,
the whole day?
Yeah.
So Kevin had a comment. I don't know if Kevin, you want to,
Yeah.
I can say.
Could you just put something in the chat?
I'll just read it. Read Jenna's comment. With UConn, the edge of the occulter won't show the atmospheric image motion.
No, we'd use a different telescope.
Oh, yeah, no, I'm in a totally different book.
Yeah, we're talking about using a guide telescope that makes an image of the disk.
Bunch of Thorlab stuff bolted on the side of the telescope.
Yeah. But it also goes to a quad, so I think we need to upgrade that to a detector, which then finds the edge of the sun and guides on the edge of the sun rather than just the quad cell, because that's quad cell is sensitive to some transparency.
I guess so.
Gradient across
But we could probably steal their engineering work,
Yeah.
bolt that on the side, run it concurrently with our existing one, then figure out how to use those signals as the feedback.
The system is very basic. In fact, the spot itself is pretty easy.
But the spot itself was golden because there were times when the spot was not happy very well and then they went into that change some of the. It was pointed better, so it's a combination of.
No worry.
uh,
It was a confusing conversation.
Especially if you're virtual.
Yeah, I don't know how you follow this.
So should we take this practicum to 10 o'clock and stop it then, so we can
Well-
have, we need to discuss the future.
Yeah, and so also I'd like to take some time for a little bit of show and tell from yesterday. I've got something I want to show. I know that Lou was finding some nice cases. Matthias was working on the thing. So I'd like to take at least a half hour to 45 minutes to.
But we're not gonna have any time to talk
We're not
about the
gonna have any
future,
time. We
which
will
is
have time.
really important.
We will, it is really important. I think we've been talking about it. We have till 12, so that's
We have to 11:45,
11:45. So that gives us 2 hours. So
and you want to take up 45 minutes.
correct. So if we do 15 minutes more of that.
Yeah.
And we can maybe do, I can show my thing, we can take a break, we can do stuff a little bit more, and then strict right at 10:45, start with discussion, or 10:30 start with discussion. That's all right.
So,
So at 10:30, we start. with
okay,
discussion.
and so then how much longer do we have for this?
15 minutes.
Okay.
Most of it, we'll watch the little circle go.
Yeah. I actually already loaded it.
Okay.
So what?
Oh,
we've got-
right now.
So like, I guess I also have
You have
the
it?
output from it. So
Yeah. I think.
Okay, that's what they do in the
Thing that
cooking
says it
shows,
will
right?
take I didn't even read that. It will take 5 minutes to read. I said we ran it sooner.
well,
I didn't read it.
And it's perfect.
I didn't even read it.
Yeah.
In one
That
second.
too.
Yeah, for me.
so this particular stage, we are going to align the data, and once the data is being aligned, you will get the cube, which is, it is going to put to what exactly the kind of what it actually found and how much is the values, and now it is kind of shifting the cubes, and so it should be over in a while.
So that RMS value, is that indicate good or bad? What is your indicator there?
So what the RMS value is actually, it is the correlation, the cross correlation.
All right, but what's your threshold for that's a good one, that's not?
Like
Uh,
estimate.
That is something what I am not pretty much sure about. What I didn't look at is like, what is the maximum value? Like,
So that's a covariance?
yeah.
What? Yeah, so is there if that was a 6, would you say, oh, I'd be unhappy, or?
So if the maximum correlation value goes like above like 2 pixels or something, then I will say, well, okay, if the data have been shifted for quite a while. It is just telling me like, okay, for all of the kind of the data frames, how much they shifts it. That which is kind of still kind of an okay region, like 1 pixel is kind of the maximum.
Oh, so this is telling what is the average.
Yeah, so an average shift across all pixels, and what the maximum shift it has actually done for any of them.
That's in pixels.
Yeah, so this is in pixels.
Okay. The cross correlation.
Yeah. And now we can do the wave angle estimation, the wave propagation angle. So in here, basically, we know that the waves are going to be traveling along the magnetic field. So if we can track the propagating waves, they're going to tell us what is the direction of the magnetic field itself. So here, there are two kind of the modes that you can actually do. Here is the full mode and the false. So like we are actually set it to the false at the moment. So if you set it to the true, it is going to take a very longer time, like around half an hour. But what it's going to do is it's going to also estimate the coherence estimates, what I actually showed here yesterday. It's going to give you the entire package what you're going to take. So if you're going to set it to the false, it is just going to estimate the planar projection of the wave tracks and stuff like that. So it's like from the wave tracking and then getting more products, you can set it to the true and wait. And if you just wanted something fast, then yeah. So what it actually does from here, like once you have actually done so far, and if you're working on your own machine, and let's say you have kind of given up, then that's fine. If you just start again from here, then all it needs is basically going to take the date, what you actually being into. So once you have the date, then what it does is like a cube V, which is your velocity cube. So you don't have to follow from the step 1 till here now. Okay, so till the de-jittering part is being done, your data products are kind of being saved. It is being saved into your folders. And now, if you just want to do this tracking, all you need is the date that you're being interested in. So if we just kind of import the wave angle kind of the code and we load the data. So it is the cube V. We are actually taking the velocity cube. The data is basically we are giving the keys and we are getting it. The header information we need is just for basically plotting it just to track what the features are. So I'm not going to get more into it, but yeah, I can just click over it and I can show what exactly it's been doing. It's going to getting the cubes and the data and everything. And
if we wanted to just change that date, would we go up a couple steps? So like we just wanted to run this code.
So till the de-jittering, if you've done, let's say for n number of data sets. Now at this particular stage, you don't have to do anything.
Oh, usually came up.
So from this particular stage, all you just need to do is to load your data, which just the date is the keyword in there. And then you've got the V is the velocity. That's it.
But we would have to de-jitter.
So if once you're de-jitter, you don't need to de-jitter again.
Right. But if we I'm thinking of a use case, like let's say I want to know how the waves look compared to the azimuth for a day I'm interested in.
Okay.
So I could bring it. I know how to bring the data over into that comp data file, like you've got it and all that. But I would have to do that de-jitter phase for that particular data set, right?
If it is a new data set.
I mean, for a different day.
Yeah. Then,
okay. Yeah. All right. So that's where I probably need some help. I wouldn't be able to just out of the box run this to look
No. So like so each and every data set you want to compare with, you have to de-jitter.
So what would be really, really helpful is to have the de-jittered version of a bunch of days available.
Okay.
Yeah.
Yeah.
And then we could just go in and grab it.
Yes. So once you have like de-jitter your number of days or whatever the dates you're interested in, then you don't have to de-jitter them all over again.
Right.
So at that particular stage, let's say you want to compare 2 of the days. And all you need to give the date 1 and date 2.
Yeah.
And load both of them and just see.
Okay, cool.
So the pre-processing is done once and then you can.
That's it. That's it.
Wait, but isn't she getting at the idea of you creating a product for us?
Yeah.
Like just save it into the.
Yeah.
Just save it into the MLSO machines somehow. I mean, if this only takes like
Well, we'll
15,
here all month, right?
if this only takes 10, 15 minutes, then on the mountain, let it run for 15 minutes after an observing.
Expert to find the region.
Yeah.
I'm declaring myself not an expert.
We've got to fix that. We've got to have it operate like on an annual, the same kind of height angles
Yeah.
every day.
The manual.
We don't have to have
But I imagine if-
intervention, number one. And on the mountain, you don't have
we don't have.
Level 2,
you don't have
yeah.
one
Yeah, level 1, and you got to process all of that.
So.
But I imagine if someone at this workshop has a day where they want to kind of look at this, right? We could talk to you over the
Yeah,
next
sure.
couple of weeks and kind
Yeah.
of get some pre-processed data.
I'm here till the end of the month, so.
Yeah. That'd be great.
But to put data in the pipeline, we really we need to make it robust and automatic. So we need to have a way to do it without selecting a region manually. And also we need to have test at the end. Look at the first and the last frame, difference in them, make sure that the alignment has actually worked.
We always, you make a movie of the the raw data looks like this, and if you've done the jittering right, it looks, like.
Yes, there you go. But in an automatic pipeline, we want something that we can pipeline can do, right?
You want a metric.
We need some kind of metric that maybe a difference image across the time series, something that the pipeline can say, okay, does the jitter work or not, right?
So meanwhile, this particular part run, I can show you for the sake of the time that what you're going to get. So once it is being done, it is going to save the wave angle into your process data. And again, you don't need, so let's say if after some time you want to check your wave angle, then you don't have to go through the process. It is already done and saved everything for you. All you can do is, again, from the comp load and the save module, you can just say the compy load angles and the plotting, and then all you need to give is wave angle is compy load angle and the date. So basically, any of the date that you're interested in, you simply give the date, and then if you just give the shape of it, then it is going to tell like, okay, what exactly is the shape of your arrays, and then you simply plot it. So this is like the wave angle is like we are having we will get two of these particular files. So one is basically the wave angles, and the second file is with the errors that it actually got. So I'm just here plotting the wave angle. So it is a 0 and all the pixels into the Y and all the pixels in X, and it is plus minus 90 because these are again the angles. And if you do it, then you get some sort of the wave map like this one. That's just so you can see the complete image. So here you can get the wave angles and all of it being estimated and done for you. So here, I guess okay, so it is already done. So I can just simply run it for you. And yeah, here it is. So it's kind of big. So now you have the wave angles now, and you want to get the propagation angle because that is all what you need, the propagation speed to estimate the magnetic field. So at this particular stage, we are not till that purpose. We are still testing the code. And like what yesterday, Richard was talking about, like, okay, we still had some sort of discrepancies from the ideal version to this one. So we are still in the process to test. However, it is still doing it, but we are kind of.
Yeah.
Yeah.
So you're not doing this for every pixel, right? It looks like you're only doing for pixel when you have a certain signal. Am I right? I mean, you have a threshold in here.
This is everything in the annulus.
So here you can see it's so
It doesn't succeed everywhere.
yeah. So it tries to get the wave. So if the wave is not propagating, it can't track. Or if it doesn't find a wave over that particular region, or let's say if you don't have the data or it's the messier data, then so the code is going to say, okay, I cannot find the track. And so in the config file, we have actually provided that what should be the thresholds over there. So till what is the acceptable limit? So it can't actually go like, okay, if it is even not in wave, just go ahead and find whatever you want. So it's not like that. We already given it the thresholds in there. So if it is there's a proper wave and it says, okay, fine, I trust it, then only it is going to show you the wave.
It's a covariance threshold, I believe. Because it for each pixel, it finds the covariance of the velocity time series with all the pixels around it.
Absolutely.
And it correlates really well where the wave is propagating.
Yeah.
And that covariance has to be above a certain threshold.
Yeah,
which I don't know if it's 0.5 or something. To be included in that fit. And it's, by the way, it's not a least squares fit, it's a least distance fit. Because least squares is a Y difference thing, and it turns out not to work at certain angles around the image. So we had to do a least distance fit, all the points to a line, which minimize the distance from that line to every point.
Yeah.
And if the coherence is really bad, then it's
Then
not
you
gonna,
can't get it.
it's not gonna do
Yeah.
something.
So this is what set the threshold for.
Yes.
Where
Yeah.
you can,
You're right. So this, so you can see on the poles, we don't have much in this particular data set.
yeah, and it makes sense. We have no signal
Yeah.
or noise.
So once we have the kind of wave angles, we can estimate the phase speeds. And here, so what we can do is we can have this particular another subcode in there, which is like the space-time run. And that is going to do everything for us. So at this time, we are not going to estimate for the entire sun because it gives some sort of very messy data. It takes a lot of time. So what we can do is or some region we have just defined in here, you can play around with it if you want. So if you run this particular code, all you need is the velocity data, the header information, the date, and if you have the bit of that outside. And we say the filter cubes, then the filter cube is also going, so what it can actually do, it can actually filter out the upward propagating waves and also the downward propagating waves. So like on that, what we can expect on the sun, that you will have both kind of like, so we do have the bulk waves, and then it can also filter out the upward and the downward component, and can also estimate the phase speeds for those particular quantities as well. So here, if you run this particular part, then we have already set the filter cubes to be false, and this is going to estimate basically the 58 phase speeds for you. But the wave angle estimation and the phase speed estimation are the two kind of the models that take a lot of time to run for the entire data set if you want to. But not like entire days. But when I say a long time, I mean like half an hour to an hour.
What shortens that time? What can, is there anything on our end that can shorten the time? Like less files or
Computational
something?
time it actually needs to.
So it's a pixel thing?
Yeah.
It's how many pixels?
Yeah.
Okay. Mhm. And this is only for comp data, not UComp?
It is for UComp as well.
Okay.
Yeah. So
Even with our changing of bits headers and stuff?
nothing. No. It will take care of it.
Nice.
So how do we tell it's comp? It figures it out.
It figures it out. So you just put the data, and then from the file name.
Is this Richard or you mostly, or is this
So-
a collaboration?
Richard writes the code, I break the code. Yeah. So then I go and like try, like, Richard, this is not working, and then like, okay, go back to your room, go try to fix it, and fix it, and then I find more bugs into it, and then he fixes it again, and yeah.
Oh.
So basically, I'm the guy who always breaks things. Yeah.
Where it fails.
We need more of those breakers. Yeah.
I can do.
So going back to, I know,
No, I mean, it's already doing it. Like, so all I can just say is like, once it's being finished, then again, you don't have to run all the code again. It will save the output again into your process files. And all you need to do is to like, again, load speeds. Like this is from the compPy IO save load. So save load has like all the functionalities. It can load your wave angles. It can load your like the forward propagating waves or the backward propagating waves. It can also load your mask. It can also load your speeds. All the kind of functionalities already in there. So once you have the save, like the save load, you can import that sort of a particular code. What you want to do, all you need is the date that you want to have. So you don't need to remember any of the other aspects that the kind of the keywords, what they mean. The only keyword you need to know is the date that you want to check. Once you give the date and you say like, okay, I want the forward propagating wave, and if I just run this thing and I plot it and I get some sort of map like that. So it is here plotting in the megameter per second. So this is the map what we're making in here.
And those marker zeros in there.
Yeah.
Looks like. So
Yes.
it didn't find anything.
Yeah, so it has more errors in there. In fact, so that is what we are being trying to see at like how the particular codes work. So once we have the phase speed, and you know the density. If we also have the density module, so we are working on it at the moment. So the code is there. I'm breaking it at the moment. So once it's been fixed, what we're going to do is like you have the density file, you have the phase speed file, you kind of simply multiply them, and you get the estimate of the magnetic field. So using the solar, the MHP kind of thing, like the phase velocity depends upon the P divided by a square root of the density. Using that sort of the relation, you can also get an idea of the plane of sky component of magnetic field. So till here we have kind of things done, and we are still working on it before we can go like fully operational out of the code.
Can you then compare the wave propagation angle with the direction of the field of the sky? Is
Yeah.
that-
Yeah.
I missed the part, I'm sorry, this is.
So the kind of the wave angles are actually telling you the kind of the topology of the magnetic field itself. So what we believe is that the waves are being traveling along the magnetic field, and since we're doing that is where your magnetic field topology looks like. So I guess like before, Steve has already kind of compared that sort of part with the magnetic field angles either.
Yeah, from the linear polar.
So
state.
what
Yeah,
really
but there's a
happens-
sanity check when you run this, if I get a wave propagation angle that's dramatically different plane of sky from only polarization, that would be a red flag, I would think.
Well, it would always be a sign of Van Vleck.
Well, no, I say bar.
Yeah, so for the compPy, we have already checked that. So we are not like in this particular session, we are not showing it, but like we have already done.
Oh, okay, so it is in the code somewhere.
Yes, yes.
Thank you.
I was gonna say, it's not, I don't think it should be assumed that the two have to coincide.
What? I'm just saying, I'm just curious if they don't, what is going on there? And obviously with Van Vleck and.
You can look at the correlation, they kind of do, but not completely, when we were looking at that
Right. But
plot
just-
yesterday, and you know, how they integrate along the line site could be different,
Right.
because think about it, you're looking at propagation of a feature in the Doppler images versus the QU integrates maybe slightly differently, so.
Yeah, it's about
Both of them are
45
structured
I mean, just
weighted
there's gotta be a-
But they're weighted differently
One at a-
because
sorry.
they,
One at a time? Are you done?
I was just gonna say, there has to be a range that you think, so there's some,
Well, they may be close for sure. It'd be surprising if they're super
yeah, I'm
different.
just saying, there's gotta be a threshold where you say, these are so far apart, I don't know.
You're thinking of using it as an error correction to say, oh.
Yeah, just,
But I don't
Yeah.
know.
yeah,
And the Van Vleck
Sanity
it'll differ by 90, and you see that other locus points. The correlation plots, Alan, you were gonna.
And we can't really compare the two because one of them is an hour and a half and we don't have the same hour and a half of polarization to average out. So you cannot make the one to one.
There's that too. There's that
yeah,
too.
but that shouldn't change dramatically.
But it's got a 90-degree ambiguity in it.
I
It
understand.
can't differ by, if it differs by 180, then it agrees to that.
Yes.
So the maximum disagreement
Barring.
is guaranteed.
We agree, barring the ambiguities in the direction.
Okay, so let's thank.
Final word on this operational piece here, you can see everything is being saved, and in case you want to download your wave angle files, speed files, whatever, and how much we there, so it is always being stored in your process data. So feel free to download and.
Excellent.
Excellent, thank you. We're gonna talk more about this.